In this session, we're going to be looking at the Combined Science Trilogy Specification Chemistry Paper 1 Higher Tier from the year 2019. We highly recommend that you download the past paper from the link below and have a go first before going through the answers in this session. In this question, we're given 4 metals: calcium, copper, magnesium and zinc, and we have to say what is the order of decreasing reactivity of the 4 metals. So the most reactive, when we're looking at the bubbles, would be calcium, then it would be magnesium, then zinc, and then copper. And if we look at our answers, the answer that shows that is this last one here. A student wants to make a fair comparison of the reactivity of the metals with hydrochloric acid. Name 2 variables that we must keep the same or must be kept constant. So the things that must be kept constant are things like the mass of the metal. We can talk about the concentration of the acid should be the same each time. There are other things that you can also say have to be kept constant. For example, the volume of the acid, the temperature of the acid, and the surface area of the metal. Now, for the next question, it says, what is the independent variable for this reaction? That means what is the one thing that we are changing each time? And the one thing that we are changing each time we do the experiment is the type of metal. For the next question, it says, predict the reactivity of beryllium compared with magnesium, and we can use the periodic table to help us. Now, if you look at the periodic table, beryllium is higher up on group 2 than magnesium. Therefore, beryllium is less reactive than magnesium, and the reason being it's going to be a smaller atom, so the electrons would have a greater attraction to the nucleus. A solution of hydrochloric acid contains 3.2 grams of hydrogen chloride in 50 centimeters cubed. So we have 3.2 grams in 50 centimeters cubed. Now the question says calculate the concentration of hydrogen chloride in grams per decimeters cubed. So 1 decimeter cubed is 1,000 centimeters cubed. So we're trying to work out how much of the hydrogen chloride we need to be dissolved in 1,000 centimeters cubed. Now, to get from 50 to 1,000, if we did 1,000 divided by 50, that would give us 20. So 50 times 20 is 1,000 centimeters cubed. Therefore, to work out how much mass we would need to do the same to the mass, which is 3.2 times 20, which would be 64 grams in 1,000 centimeters cubed. So that's grams per decimeters cubed. This question is about salts. Ammonium nitrate solution is produced when ammonium gas reacts with nitric acid. Give the state symbol for ammonium nitrate solution. So the hint is there, solution, which means it's dissolved in water. Therefore, the state symbol should be AQ for aqueous. What is the formula of nitric acid? Now, if we look at each of these, the first one is hydrochloric acid, the second one is nitric acid, this third one is sulfuric acid, and this last one here is ammonium hydroxide. Ammonia gas dissolves in water to produce ammonium solution. Ammonium solution contains hydroxide ions, which are OH minus ions. A student adds universal indicator to solutions of nitric acid and ammonia. What colour is observed in each? Now, if we look at the first one, this one here is an acid, so the colour we should observe is red. We'd probably accept an answer of orange or yellow here for weaker acids. For colour of ammonium solution, now ammonium solution is an alkali, therefore we would observe a colour of purple, and again different shades of blue or dark blue should be accepted here also. The student gradually added nitric acid to ammonium nitrate solution. Which row A, B, C or D shows changes in pH when the nitric acid is added in excess? And that's important. So first of all, if we're starting off with ammonium solution, we're going to start off with something which is alkali. So it can only be answers A or D. Now, if we keep adding acid to the alkali, first of all, it will become neutral, which is pH 7, but then if you keep adding the acid in excess, it will end up being acidic, which would be pH 2, so the correct answer is D. Calculate the percentage by mass of oxygen in ammonium nitrate. Relative atomic mass for the individual atoms are hydrogen is 1, nitrogen is 14, oxygen is 16. The relative formula mass of the whole molecule of ammonium nitrate is NH4NO3, which has a mass of 80. So percentage of oxygen, we can see that we have 3 oxygen atoms. So we've got 3 oxygen atoms, and the mass of each oxygen is 16. So 3 times 16 is 48, which means 48 out of the whole molecule mass of 80 is going to be our oxygen. And to make that into a percentage, we would then times the answer by 100, and that gives us 60%. So 60% of the oxygen in ammonium nitrate is oxygen. In this question, we are asked to describe a method to investigate how the temperature changes when different masses of ammonia are dissolved in water. Now, I always think it's easier for me to know what I'm doing if I draw myself a little diagram. So when I write my steps, I know exactly what I'm writing. So in this experiment, we would use an insulated either test tube or boiling tube or beaker, because we don't want the heat to escape. We would then put a known volume of water into, in this instance, the boiling tube, and take the initial temperature of the water. We would then add a known mass, so for example, 2 grams of the ammonium nitrate to the test tube, and we would record either the highest or the lowest temperature that the water changes to. We would then calculate the temperature difference between the starting temperature and the final temperature, and then we repeat the experiment using different masses of ammonium nitrate being added to the water each time. So for example, we might do the first experiment using 2 grams of ammonium nitrate, then 4, then 6, then 8, and then 10 grams of ammonium nitrate. And we record the starting and the final temperature each time. This question is about oxygen. Hydrogen reacts with oxygen, and we have our equation showing 2 hydrogen molecules react with oxygen to produce 2 water molecules there. And figure 2 shows the relative energies of the reactants and products at a certain temperature. And we've got to label the activation energy on figure 2. So the first thing that we would do is we would draw a line across from where we have our reactants, and then the activation energy is from the highest point on the curve to the line from the reactants that we've just drawn. So if we draw our line here, this here is our activation energy. Now for the next question, 3.2, we've got to determine the overall energy change. Now to do that, we need to work out, and that will be in our kilojoules. So to do this, we need to work out the energy of our reactants here is 800 kilojoules, and the energy of the products here is 300 kilojoules. Therefore, the overall energy change is we've gone from 800 to 300, so 800 take away 300, and that gives us an answer of 500 kilojoules. To determine the overall energy change for the reaction between hydrogen and oxygen, we use the energy diagram here. So we can see that the energy of the reactants was 800 kilojoules, and we take away the energy of the products, which was 300 kilojoules, and that gives us an energy change of 500 kilojoules. So our answer is 500 kilojoules. Now, oxygen is in group 6 of the periodic table. Figure 3 shows the outer energy levels of a molecule of an O2. draw the electrons in the outer energy levels. So we'll use our dot and cross diagram. So for this one, we know that each oxygen has 6 electrons on the outer energy level. So we've drawn our 6 electrons for our first oxygen atom, and then we'll do the same for our second oxygen atom. And there we have it. So you end up with a double covalent bond between the 2 oxygen atoms. Now for this question, we have to calculate the overall energy change for the reaction. And the overall energy change for the reaction is going to be the total bond energy of the reactants take away the total bond energy of the products. So if we look at the reactants to start off with, we can see here that we've got an oxygen to hydrogen bond, another oxygen to hydrogen bond, so that's 2, but because we've got 2 molecules, that's going to give us 4 oxygen to hydrogen bonds, and we have an oxygen to oxygen bond there, but again, because we've got 2 molecules, we've got 2 oxygen to oxygen bonds. And then for our products, we can see we have an oxygen to hydrogen bond there, an oxygen to hydrogen bond there, but we've got 2 of these molecules, so we have 4 oxygen to hydrogen bonds. And then for our second product molecule, we've got an oxygen to oxygen double bond, so that's just 1 oxygen to oxygen double bond. Now if we use our tables, that is going to be 4 times our oxygen to hydrogen bond, so that's 4 times 6, 463, plus 2 times our oxygen to oxygen single bond, so that's 138. And then on our product side, we've got 4 times our oxygen to hydrogen bond, so that's 463, plus an oxygen to oxygen double bond, so that is 496. And if we total the energy of our reactants, that gives us 2128. And if we total the energy of our product bonds, that gives us 2348. And the overall energy is the reactants take away the products. So it is 2128 take away 2348. So the overall energy change is minus 220 kilojoules. This question is about elements in the periodic table. What order did scientists use to arrange elements in the periodic table? So in the earlier periodic table, the atoms were arranged by atomic weights. In the early periodic table, some elements were placed in the wrong groups. Mendeleev overcame this in his periodic table. Give one way that Mendeleev did this. So what Mendeleev did was, for atoms that had not been discovered yet, he left gaps. Explain why the boiling points in table 2 are low. Now, if we think about this, the forces between the molecules are weak forces, therefore little energy is needed to overcome these forces. Explain the trend in boiling points in table 2. So as we go down the group, the molecules are becoming larger. Because the molecules are becoming larger, the forces between the molecules increases. So therefore, the boiling points will increase down the group. Explain why neon is unreactive. Give the electronic structure of neon in your answer. So neon is unreactive because it has a full outer shell. And then what we do is we just give the electronic structure of neon, which is 2 in the first electron shell and then 8. How many atoms are there in 1 gram of argon? So the Avogadro constant is 6.02 times 10 to the power of 23. So that's how many atoms there are in 1 mole. the relative atomic mass of argon is 40. So in 40 grams, we would have 6.02 times 10 to the 23 atoms. Therefore, to work out 1 gram, it would be 6.02 times 10 to the power of 23 divided by 40, which would tell us how many atoms in 1 gram. And if we work that out, we get an answer of 1.505 times 10 to the power of 22. This question is about electrolysis. Some metals are extracted from molten compounds using electrolysis. Why is electrolysis used to extract some metals? So we use electrolysis when the metal we're trying to extract is more reactive than carbon. Aluminium is produced by electrolysis of a molten mixture. What two substances does the molten mixture contain? So when we're extracting aluminium, we first off have the aluminium compound, which is aluminium oxide. But also we add cryolite to reduce the temperature at which the aluminium oxide will melt. Copper and chlorine are produced when molten copper chloride is electrolyzed. Complete the half equations for the reaction at each electrode. So if we start off with a copper ion, we've got to add 2 electrons to make it into the copper metal. And if we've got 2 chloride ions to produce the chlorine gas, each of the chlorine ions will have an electron taken off. So because we've got 2 chloride ions, that's 2 electrons that will come off. Figure 4 shows the apparatus the student used to electrolyse copper chloride solution. So we've got copper chloride in the solution and we've got pure copper electrodes. The student measured the mass of the copper deposit on the negative electrode after 60 minutes, and then he compared the mass deposited with the expected value. Suggest 2 reasons why the mass deposited was different from the expected value. So the first reason could be, for those of you that have done this experiment in school, we know that when we do electrolysis of copper chloride solution, all the copper doesn't stick to the electrode, some of it falls off, and we get a little deposit at the bottom of the container. So that could be one reason. The second reason could be when the student has dried the electrode and reweighed it, it might not be completely dry, so we're weighing some of the water as well as the deposited copper. Figure 5 shows the expected mass of copper produced each time when we do an experiment where we're electrolysing copper chloride with copper electrodes. So what the diagram shows is our expected mass of copper in milligrams, and that's after certain amounts of time. So we've got to determine the mass of copper after 24 hours. So what we can do is we can work out how much mass is produced in 30 minutes, and that is 5.4 milligrams in 30 minutes. So if we got 5.4 milligrams of copper produced in 30 minutes, to get to 24 hours, okay, so 30 minutes is half an hour. So to get to 24 hours, we would have to times 30 minutes by 48, and that gives us 24 hours. So then if we times our 5.4 milligrams by 48 as well, that will tell us the mass of the copper in 24 hours. And when we do that, we should get an answer of 259 milligrams produced in 24 hours. That's 259 milligrams produced in. Silver nitrate solution is electrolysed. Figure 6 shows the change in mass of the negative electrode after 10 hours. So determine the mass of the negative electrode at the start of the experiment. At the start, we're looking at 0. So we've got to work out what this is here. So we can see that every 2 squares is 1 gram. And we can see that our point that we're trying to work out is in between the middle of that last square next to 5, so that would work out at 4.6 0.75 grams. Now, calculate the gradient of the line in figure 6. So the gradient is going to be the change in y divided by the change in x. So if we look at our graph, the change in y is we've gone from 4.75 to 6.75. So that is 2 divided by the change in x. We're going up to 10 hours here, so 2 divided by 10, and that gives us 0.2. And because we've got grams divided by hours, our units are going to be grams per hour. So our answer is 0.2 grams per hour. This question is about sodium. Sodium reacts with chlorine. What is the balanced equation for the reaction? So if we look at this, chlorine to start off with is Cl2. So it's got to be one of these two, which is the correct balanced equation. And the formula for sodium chloride is NaCl2, so this would be the correct balanced equation. And we can see we've got 2 sodiums to start with and 2 sodiums at the end. We've got 2 chlorine atoms to start with and 2 at the end. So for question 6.2, hot sodium is put in a gas chart of chlorine. Describe an observation made before, during and after the reaction. So before the reaction, we start off with a grey solid metal, and also the chlorine gas is started off as a green gas. During the reaction, we should see an orange flame indicating the reaction is taking place. And at the end, we're going to end up with sodium chloride, which is table salt, which is a white solid, or we could say powder. So in this question, we need to explain why sodium is less reactive than potassium. So first of all, what we need to say is that sodium is higher in group 1 than potassium. So this means sodium has less electron shells than potassium. This means its outer electrons are closer to the nucleus. And this means there's greater attraction. Now, if there's greater attraction of the outer electrons to the nucleus, they're going to be less easily lost. In this question, we're told that chlorine reacts with sodium and hydrogen, and when it reacts with sodium, we get sodium chloride. When it reacts with hydrogen, we get hydrogen chloride, and we need to compare the two in terms of structure and bonding. So what I would do for this question is I would divide your page into 2 so we can clearly show what the similarities and differences are. So to start off with, if we're going to look at bonding, sodium chloride has ionic bonding, and that's between metals and non-metals. However, hydrogen chloride has covalent bonding, and that's between 2 non-metals. So that's one of the main differences in terms of the bonding. What that also means is that in ionic bonding, we have charged particles, so the ions, whereas in covalent bonding, has no charged particles because it's between the atoms. Okay, now in terms of similarities, we can say that ionic bonds are strong bonds, and the covalent bonds are also strong bonds. Let's just make this clear where we're doing our comparisons. Okay, so now if we turn our ideas to the structures. Okay, for sodium chloride, we have a giant ionic lattice, whereas for hydrogen chloride, we have simple covalent molecules, and therefore there are going to be strong electrostatic forces between the ions in sodium chloride, whereas in hydrogen chloride we would have weak intermolecular forces between the molecules. So we need to make sure we don't get confused here. So between the atoms in the molecule, we've got the strong covalent bonds, but between the molecules, we have the weak intermolecular forces for hydrogen chloride. And with sodium chloride, we have the giant ionic lattice, so we've got lots of strong electrostatic forces between the ions. And that there should be enough to get you your 6 marks, because we've done similarities, we've done differences, and we've compared bonding and structure.